In this video, we're going to continue talking about linear models, but we want to talk about the other methods for creating a linear model. So most of the time, we're given raw data, and we put the X data into L1, and we put the Y data into L2, and then we use a linear regression function I think we use something like what is it, stat calculate 8, and I think it's linear regression function, and we give it L1 and L2, and it comes back and it gives us the A value and the B value, and whatever those are, we get those, and then we have the equation y hat equals A plus bx. So this is the one that we focus on the most, and there's other videos to see how to do this, and we've practiced this in class. What we haven't done is talk about these other ones a lot. Now, you've had homework problems, so hopefully you've figured it out. But one is to read the computer printout, and that is explained on page 188. And then the other way is to use the formulas. We use the formulas when we're given some summary data. So what I want to do in this video is I want to talk about 1 and 2 to make sure you know how to do those, because those will show up on a test. So the first one, this is where we're going to use the formula. And so I want to show you a typical question. So notice in this question that you're not given a set of data. So we don't have any raw data. But what you are given is R. And you're given some summary data, some means and averages, and you're given some standard deviations. So let's just read this real quick. A study of grasshoppers discovered that there is a moderately strong linear correlation with R of 0.832 between the number of chirps per second and ground temperature. Their study uncovered a mean chirp rate, so chirps per second, of this 16.567 with a standard deviation of 1.713 chirps, and an average ground temperature of, and I'm pretty sure that this would be degrees, of 79.347 with a standard deviation of this. So what is a linear model for predicting ground temperature? So I'm going to make a little picture for myself. Ground temperature, and this would be chirp rate. Okay, so we have some relationship. Okay, so what we know is we know that from our formulas, we know that y equals b0 plus b1 times x, predictor value. This is the same, there's nothing different than a plus bx. We just use slightly different notation when we're using the formulas. It's no big deal. So the slope is b1 is r times the standard deviation of the y values, so the predictor values, divided by the standard deviation of the x values. Okay, so if you had the raw data and you put it into L1, you could use one variable statistics and get these standard deviations. By the way, what that means, just in case it comes up on the test, which if I bring it up, it's very likely that it will somewhere, is that if we think of the slope as if you go up, one standard deviation or you move 1 standard deviation in x, 1 standard deviation in x, the model changes by r standard deviations in y. So that may come up sometime, if it either goes up or if it could go down. If you change 1 standard deviation in x, you go down r standard deviations in y if it's a negative slope. Okay, so what we want to do is we have a formula to calculate this, or we have the information. Let me go ahead and put the y-intercept. That's x bar minus b1 times, that y bar minus b1 times x bar. So we need to calculate b1 first, and then we can plug it in here and calculate b0. So we have r up here. R equals 0.832. Y, or let's go x bar, because at chirp rate, the chirp rate is 16.567, and y bar is 79.347 degrees. And then our standard deviation in x is 1.713, and our standard deviation in y is 7.020. Okay, so my slope would then just be, or r slope, 0.832 times the standard deviation in y, 7.020, divided by the standard deviation in x, did I say 7? It's not 7. Oh, it is 7. 1.713. Okay, sorry about that. It's a little confused. Let me do this real quick on a calculator. So I'm going to just pull up my calculator. 0.832 times 7.020 equals, divided by 1.713, and we get 3.409597. Okay, so a lot of resolution there. Okay, so now B0 is just y bar 79.347 minus 3.409597 times x bar 16.567. And so let's go to the calculator again. Clear 79.347 minus I just realized this calculator won't work. Oh, it is in scientific mode. Okay. Minus 3.40959 times 16.567. Okay, so we get what was it? 22.860. All right, so therefore our model, and I guess I better write it properly. So ground temp with a hat equals 22.860 plus 3.409597 times the chirp rate. Okay, so that's how you would create the model. So obviously you could do it a lot faster than what I did. What's important is to show, you probably should show these equations. So you're showing the reader that you know these equations here. Show this step right here, and show this step right here, and then write this. That's the most important. You don't have to, certainly you don't have to draw this stuff over here, and you don't have to label all this stuff. It helps. It's a good idea to do it. If you make a little calculation mistake somewhere, but you've shown all this work, then I can see that you know what you're doing. You just made a little typo or something with the calculator. Okay, so that's how you use the formula. So real quickly, you could also get computer printout. And so I want to go over this. And again, it's really well done on page 188. Now again, you don't have raw data, and then later, sometimes what you'll do is you'll be given the computer printout. You might be given the scatter plot, okay, and you might also be given the residual plot. So this is a quick way to get you thinking and using the model in some way without having to make you go through all the calculator gyrations. So here, let's talk about this. So first, they tell us what the dependent variable is. So that's our y variable. Okay. They tell us that r squared is equal to 0.6922947. So r would be the square root of that. So let's just look real quick. We don't have to do this, but let's just make sure we know what we're doing here. So we could type that in, 0.6922947, and we take the square root. Now remember, that's plus or minus. So let's see, 0.0832, 0.832. All right, so in this case, the relationship is going up, so it's going to be a positive. All right, I'll show you how you can tell that. Now here, S is the standard deviation of the residuals, but the computer printout can't put an E there. Remember that E stands for the residuals, the observed value minus the predicted variable. So you could have an average value for the residuals. Here we have a standard deviation of the residuals. In other words, if we plotted the residuals, I don't know, they're not always unimodal, but if they were, then we would know that sort of 3 standard deviations in one direction and 3 standard deviations in another direction would cover almost 100% of the residuals range. Okay, so this is the standard deviation of residuals. Now, the most important thing is, see, this says variable, so we have a model, y hat equals a plus bx. So the constant variable, remember this is a 1 here, and this theoretically has a 0 right there. We don't write it. So this is think of this as a constant variable. So the y-intercept, when it says constant, that means y-intercept. Okay, so our y-intercept is right here, the coefficient. That's what these numbers are in front of the variables. So the coefficient, the constant coefficient is right there. So y hat equals 22.84898. And then here, chirps per second, this is the independent variable. If this is the dependent variable, so other language in math, this is the dependent. variable, and this is the independent. We don't like that language in stats, but we inherit it here for the computer printout. So we know that this is the slope. Right there, that's the slope. So that's B. So we have 3.410323 times x. And of course, we want to write that the way we did above. Ground temp with a hat equals 22.84898 plus 3.410323 times the chirp rate. So there's our model. So again, you can do this a lot faster. Now, all this other stuff over here, I didn't even put numbers, but there may be numbers here. Ignore those numbers. Don't even worry about them. We'll use a few second semester. So at this point, don't even consider this stuff. You're only interested in the y-intercept and the slope. These numbers right here, the coefficients for the model. Okay, that's the end of this video. Again, there's 3 ways to create a linear model, and I just wanted to make sure that you were comfortable with these other 2 ways that are not quite as common. Good luck.